Yeah.
Okay. So now I'm sure I will not pronounce them correctly. We have two speakers presenting together, and that's Ramakrishnan Arul Babu and Madheshwaran Lakshmipathy. Sorry,
That's perfect.
I'm
That's
sure I had it horrible. So they have a different background. Ramakrishnan has a background in sustainability in buildings, while Madheshwaran in electrical and electronics engineers. But in common is that they are enrolled in the DTU program of wind energy, and they've been part of the team racing with the small wind turbine at a small wind turbine competition and winning, if I'm not mistaken, right?
yes, yes.
Yes.
Oh, yeah, we are happy to have you here and to hear about your achievement. And you should be able to share the screen now.
Yeah. Okay, just a minute. Oh, I Ramakrishnan, are you sharing?
Yeah, I think I can share if you want.
Oh, okay. Sorry, I was keeping on muting you. I didn't know who you were.
Oh, that's okay. That's fine.
I will just mute all the others, so you two will need to unmute yourself again.
Yes.
Yeah.
And then,
Can you see my screen?
yes.
Okay. So
Yeah. Thanks. Go ahead.
yes. Yeah. Madhesh, you would like to start? I think Madhesh is muted, I guess.
Oh, it's with the host.
Yeah,
Can
yeah,
you,
no.
huh?
Yeah. Madhesh, you can start now.
Okay. So, hi everyone. So, we are here to demonstrate our research, which was focused on winglet blade design and the control for ISWTC. So, international small wind turbine competition, which occurred in this year, and it was more of focusing on the optimizing aerodynamics and performance. So, we are just two students representing the eight students, the whole team, and this also a course and a club as well as supervised by Supervisor Robert, Tesong, and Mac. So we are in this course. We are focusing on two different competitions for on international small wind turbine competition and racing alias. So racing alias is nothing but capturing wind and using a wind car for driving. It's both of them are occurred in Netherlands, and this is the both competition, and you can know the purposes. This is our team. So you could see the winglet hot with the high winglet profile and which is been demonstrated at TU Delft. Okay, next slide, please. So getting into ISWTC, so it's a student competition where we have to design, model, and build our own wind turbine, and not only the wind turbine, and also the control part and every aspects of that. And so our main motive is to test it in TU Delft wind tunnel, and it's conducted by Hans University of Applied Science. So we presented over there. So we got so key parameters for the evaluation is like performing the low cut in wind speed and maximum electrical CP and highest type AEP which we have to demonstrate. And there are two reports, which is a technical report, which the aerodynamic and aerodynamic simulation design and manufacturing everything. The main reason for the competition is the sustainability and the parameters which we have been incorporated and according to the small wind turbine which we have been developed. We got a good result from this year. So we won with the lowest cut-in wind speed of 2.5 meter per second, with highest electrical CP of 0.408 and highest AEP. You can notice then.
Okay. So I'd like to talk about what are the new changes that we made for the new ISWTC 2024. So the first is that we have modeled a winglet blade with 80-degree downward winglet, which is like almost like 20% of the blade span. And the reason is because the rotor area is like limited to 2 square meters. So we have a boundary condition. So we will not overcome the boundary condition to increase the CP. So we have gone with the winglet design. So other parameters that we did for this year was like we had active pitch control and with RPM and pitching sensing. And then we also had like a wireless wind measurements for automatic calibration. And we used a BIM approach for aeroelastic simulation for the winglet blades. And for doing the winglet blade design, we used a lifting line framework. So because we found out like the BIM framework was not compatible to find out because the BIM framework failed to do the design when if it is not then there is a radial so for a non-planar rotors, so which was a little difficult to do it in BIM. So we used a lifting line framework. So the inputs for the first part of the design, what we gave was the lifting line geometry, the circulation, the tip speed ratio, and the CL by CD ratio. And the outputs what we got from the first, like we solved it iteratively and to solving for the highest CP, to increasing the CP. The outputs what we got from the first part was like the loading along the blade span, and like we got induced velocities and wake geometry and coefficient of the CP. So for the second part of the design, so we give additional input, something like we fixed a aerofoil profile, which is the SD7032, and we had a design angle of attack. And the outputs what we got from the second part of our design was like the lift distribution along the lifting line geometry, the chord length, and the generalized twist. So as you can see from here, so this is just a wake profile around the winglet blade, and this is nothing but the forces what we actually computed for a winglet blade, which is almost like the centrifugal forces are predominant in the winglet of the rotor. So which is like almost like 10 to 20, 13 times more than the normal loads on the blade. So for the aeroelastic simulation, there is no present tool which actually can do lifting lines framework simulation for doing aeroelastic simulation. So that is not possible for us. So we used a BIM framework tool, which is nothing but Hawk2 for an analysis. And the main assumptions what we have was like the flow we kept it as steady, and the tower and blades we kept it as stiff. The wind speeds what we analyzed was like around 4 to 10 meters per second, which is what we generally use it in our wind tunnel testing. So that's we kept it till 10 meters per second. So from the aeroelastic simulation from Hawk2, the main results what we got was, so the radial loads, which is predominantly seen only in the winglet blade, this is because of the centrifugal forces that's acting on the winglet. And the tangential load, which is seen here at the end, so which is nothing but this tangential load on the winglet is opposite to that of the, the main part of the blade. This is actually quite which is quite a decent thing, because like we were not sure like whether the BIM framework could handle the centrifugal loads and even the opposing tangential loads in the winglet design. So another part of the next part what I want to discuss about is the winglet manufacture. So we used a carbon fiber because which has like the high strength to weight ratio, and we used epoxy resin as a binding material for it. And from our winglet design, we actually have the two molds which is seen here, these are the negative molds of the pressure side and the suction side. And the different carbon fiber textures we used was like the unidirectional, and we also had like a 45-degree, which is for the torsional stiffness and also for the blade root reinforcement. So I just wanted to show you some pictures about like how we did the winglet manufacture. So this is like the winglet after, as soon as it's comes out of the mold from the vacuum section. So we get this mold and we cut it, and then we use reinforcements like webs and shear webs along the blade span, and then we actually stick the positive and negative side of the pressure side and the suction side using the structural probe. So the next part of the analysis was like the sustainability, because we need to see how the small wind turbines what we are actually producing is can contribute to the society. So we have taken a case in Kapota, South Sudan. So where actually it's one of the places in the world which has the lowest electrification rate. So we actually assumed a small wind turbine can purify the water to provide fresh water to the occupants over there. So we consider the occupants to be around 10,000. So the requirement is like 7 liters per day per person. So the total requirement for purified water was like around like 70,000 liters. And we calculated as per the lifting line framework. So the mechanical design CP was like around 0.468 for the non-winglet rotor, and for the winglet rotors like around 0.4518. So which is like almost like 11% increase in the CP. And we computed for the design scale electrical CP was like for the non-winglet rotor was like around 0.41, and for the winglet rotor was like around like 0.453. And the energy produced from the small wind turbine for a winglet rotor was like around 3 kilowatt per day. And the energy actually what is required to purify the water was like around close to 14 kilowatt hour per day. So the number of small wind turbines required is just like around 5, but like it can save carbon emissions of almost like 7 tons throughout the lifespan of the small wind turbine. So this is the computation we did, and we just showed the sustainability of the small wind turbine. So next part.
So by seeing the picture, you could notice that it's a collective pitch system. So we have used a single stepper motor in front, and using it for the three bevel gears connected with the intergear, and for the roll gear for the pitching system, where we have a 360 rotation flexibility, which is not used, but it was completely automated and using the controller. Next slide. So the application, if you can see in the right time top picture, this is just the operation strategies which we followed for according to the small wind turbine. And you can see the more critical stage was the optimization zone, from starting from the low cut-in wind speed to the rated limitation zone, what we are using to the rated wind speed. And so here we used a basic circuit. Let's say we implemented a basic circuit using the Arduino microcontroller. But first, we created a Wi-Fi gateway to interconnect with the wind measurements, like a model predictive control, where we get the live measurements, and we also give our own measurements according to that. So it intellect and also analyze the wind gust, what's happening in the tunnel. And with the help of the proximity sensor, we were able to get the instant RPM measurements. So without any torque control, we were able to measuring the RPM and getting the torque according to that. We were able to doing the finding the optimum pitch angle to increase the optimum performance and maintaining the tips per ratio lambda. So in here you can notice that this way we're able to immediately from cut-in wind speed to increase the lift, and immediately changing it to the operation range in the pitching was able to achievable in this strategy. And also we were having aerodynamic brakes in the cutout, so we were so confident about that. Next slide. So this is the new control design which we are planning to implement on the next year. So this here you could notice there are three different regions we are focusing on. So from, of course, the power limitation zone is the region 2, and the changing here the two first one is of course the torque control, which is the proportional controller, and the other two is the PI controller. So if it's the most critical part, we were not able to find the maximum part. So that's why we were following this strategy right now. So finding the optimal efficiency at the rated wind speed. So finding the integrated and the torque control for the requirement of the finding the optimum pitch was the hardest thing which we were finding difficult. And then in the region 3, where the limitation zone, according to that, it's a pitch control, where for the each wind speed and requirement of this one, we can able to demonstrate that. Next. And this is the generator, and we are having a radial flux generator which is completely in-house manufactured. And we are currently using the low resistance for the torque control, but we are trying to make an extension system for the control of the turbine as well.
Okay, so this is the measured result what we got from the wind tunnel testing at TU Delft. So the first result what we see here is like the 0.518. This is the aerodynamic CPU what we actually computed from our design and simulation. So which we expected to be like around 0.518. And we found out from our generator testing, which is like this is the generator testing rate. We found out the generator efficiency was like almost like close to 80%. So we expected the design electrical CPU was like around 0.4092. But we got a electrical CPU from the measurement like for 0.408, which was very close to it. And the total annual energy production AEP, which we computed, was like around 1263.7 kilowatt hour. And the cut-in speed we assumed to be like, it was like from design, it was like 2.5 meter per second. From the testing, we found out it was like around 3. So it was very close to what we actually computed. And this is just the power curve of like, this is the maximum CPU curve, which we expected to be. And this is the measured power curve, which we did it in the wind tunnel testing at TU Delft. And we just wanted to show a small video of like our okay, I think audio is not visible. Audio is not here. I'm not sure. Okay, I think there is. Okay, we can just see how to do the pitching, and then we just see the working of the. Sorry.
Just play that.
Yeah. Sorry. Yeah.
This is Tesong, our professor.
So this was just running at the full speed, and then we used the aerodynamic brake to just pitch out the blades to keep it to bring it to peak. That's what we did here right now. Okay. I think it stopped. I don't know. Okay, so I'm sorry. I think there is something wrong with the video. Yeah, sorry. Yeah, thank you. That's it.
Now you can clap. Thank you very much. Questions from the audience?
I think we got a question.
There is one question from David. Just a moment that I... yes, now you can unmute yourself, David.
Okay, can you hear me?
Yeah.
Yes.
Okay, thank you for that presentation. It's a very interesting competition. I was a judge in it for 1 year and had a really good time seeing what the students were producing. Okay, my first question is what is the design tip speed ratio of your turbine?
Yeah, so the design tip speed ratio is like 4, but actually from our wind tunnel testing, we found out it was like not close to 4, but it was around close to 4.5.
Okay, in terms of maximizing your CP.
Yes. So the maximum, the design CP was like what I said was like around 0.518, and we got the optimal TSR was like around 4.
If I make the statement that blade tips are going to be more effective at low tip speed ratio, does that make sense to you?
Come again? The blade tips are more effective.
A typical design tip speed ratio for a small turbine is 7 or 8, not 4.
Yes. Yeah.
Okay, so I would say that if you added wingtips to a blade at a tip speed ratio of 8, they would not be as effective as if you added them to a blade with a tip speed ratio of 4. Would you agree? Would you agree with that statement?
So I would say like the non-winglet rotor. So what we found out that the optimal TSR tip speed ratio was like around 5, but with the for a winglet rotor, actually here which the main objective for us was like increasing the CP, which we did like so that the tip speed ratio has come down to 4. And the main reason to have that winglet rotor, one was like to optimize like increase in CP. Other one was like to reduce the tip losses. That's what we actually tried to do. And actually, if we actually had a winglet to the let's say we have winglet rotor, right? So which actually increases the induced drag. So which actually creates like if the tip speed is more, so which will create more drag to it. So we found out like so the optimal tip speed ratio was actually come down to instead of 5 or 6, it has come down to 4 for us. That's what we actually understood from that.
Okay, but that didn't actually answer my question about the effect of tip speed ratio on the effectiveness of winglets. Possibly it's one that would take more time to discuss than we have available, so I might shut up at this point and let other people ask some questions.
Okay. Okay. Sure. I think we can mail you like if we with our understanding what we have. Thank you.
Oh, I think your supervisors are very good aerodynamicists. They can have this discussion with you.
Yeah. Thank you. Yeah.
Any question? Yeah. Just come a little closer. It'll be too difficult for the mic.
Thank you so much for the presentation. But so my question is, has there been any other consideration of using more sustainable materials other than carbon epoxy?
Actually, to be true, yes. Actually, we have considered flax fiber as well as an alternative. But like the thing is that we didn't have a lot of time to work with because like from the previous year we used flax fibers and we were not able to get some good surface finish. So because of which our designs, our electrical CP came down. So we didn't want to make the same mistake. We just wanted to see if the winglet actually was performing as per our design. Maybe in the future years we are thinking actually to go with the alternative materials like flax fibers, or even want to check like glass fiber as well. But yeah, that's in consideration. Yes.
Yeah. Okay. So if there are more questions, then I guess you can talk to them a little later, or you can also put in contact in your presentation. I don't know if there will be your email addresses. Can I? or can you put them maybe if someone wants to ask questions?
Yeah, we can put them in the chat if you
Yeah,
want.
just put them in the slides and then we upload the slides. Don't worry.
Okay, yes, we'll do that. Yeah, thank you. We'll put it in the slides and send it to you. Thank you. Thanks a lot.
Thank you very much.
Yeah, thank you. Thank you for this opportunity.